All right, good morning. Happy Friday. I hope the test went okay. I haven't looked at it, so I don't know anything that's going on with it, but I hope everything went okay. First announcement, WebEx changed their user interface, and I personally don't like it. I have talked to the technical people saying, talking about the way the interface looks. But you as a viewer, you want to either have the thumbnails at the top or the thumbnails on the side to be able to see me best. I have looked at the videos on YouTube and it does show a full screen of me, so they do look okay. But I'm just letting you know, if things seem weird, it's because WebEx changed their user interface. Okay, the second announcement is some of you got a notification about taking a pre-calculus bridge class over the summer. And if you would like to meet with me regarding that, I do want to give you the advantages and the disadvantages, and this is going to be my personal opinion. So if you want to meet with me, we can absolutely do that. In fact, yeah, today might be hard. I'll send out a remind message. How's that? So I'm going to send out a remind message about a meeting that I'm going to have. It'll be after school sometime. Maybe not today, maybe Monday, regarding that memo or that email that you got regarding the bridge class. And I'm going to give you my opinion on advantages of it and disadvantages of it. Okay? All right. Today, I'm teaching a new lesson, 15.1. And we're actually going to be talking about the inverse of the exponential functions, and it's called the logarithmic functions. So we're in lesson 15.1. And it's defining and evaluating a logarithmic function. It's California Common Core Standard F.BF.5+, and that plus means honors. And I do want you to do the explore. We're going to actually do it together. And I want to say that a logarithmic function is the inverse of the exponential function. All right. So I want to look at f of x is equal to 2 to the x, and that's what you had your test on. That's exponential growth. And its inverse looks like inverse of x. It's log base 2 of x. And that's how you read it, log base 2 of x. So the base of the exponent matches the base of a logarithm. Now, one thing about this is there's 3 different levels. You have a subscript. You have something that's along the same lines as the log or inside the logarithm, and that's a superscript. So make sure you're really careful about how you write things. So the way you would read this as log base 2 of x cubed. So log base 2 of x cubed. So what I want to do is I want to graph this guy, and then we're going to graph the inverse, and I want you to see the similarities. All right. So this parent, we picked the points. We picked a 1, 2 to, or sorry, we picked a 0, and 2 to the 0 was 1. And we picked x equals 1, and we got a 2. And remember, this guy has a horizontal asymptote at y equals 0. So the horizontal asymptotes of the exponential growth and decay are y equals 0, and what moves it would be the k. And when we graph these, 0 up 1 is there, and right 1 up 2 is there, and this is an exponential growth function. And we know that the domain is forever left and right, and the range is up forever from 0. I have an orange marker somewhere. See if I can find it. Okay. So for the inverse, if you were going to find the points, there's a couple of properties that you need to know that I haven't taught yet. So one of the properties says this, I'll write it down here, that log base of something of 1 is always 0. So this could be log base 7 of 1 equals 0, log base 9 of 1 equals 0, log base a half of 1 is 0. So B just, it can't be, this has to be greater than 0, but it can't be 1. Okay, so if we pick 1, log base 2 of 1 is 0 because of this property. So notice I'm not picking 0 because we don't know anything about log base 2 of 0. But there's another property that says this. Log base b of b to the x equals x. So if I pick a 2, log base 2 of 2 to the 1 is 1. Did you follow that? Log base 2 of 2 to the 1 equals 1. Now, did you guys notice anything about this? They just switched, right? Remember we talked about that, how inverses switched, see how the points switched? They switched, right? And instead of having a horizontal asymptote, it has a vertical asymptote at x equals 0. And what's going to move a vertical asymptote is going to be h. So when we graph our point, well, let's graph the inverse. I'm sorry, the identity. Remember the identity that cuts the graph in half? And it's called the identity because y equals x. If you graph this right 1, 0, right 2, up 1, the inverse runs along the asymptote like that, and that's the logarithm. And if you can see, it's a reflection over the identity. Now, the domain for this guy is from open on 0 to infinity, and the range is forever up and down. So what do you notice about that?
They switched.
Yeah, the domain became the range and the range became the domain. So not only do the ordered pairs switch, x and y, they switch, the domain and range switch. So this is what the logarithm looks like in a graph. All right, we're going to start the lesson now. This was in the Explorer. These two properties, I'm going to teach these properties later on, but you need these two properties. If you're being asked to graph, you need these two properties to come up with the 2 points. Because what if you don't have this? You can't just look at it and switch it. You have to know how to come up with the points using these two properties. You guys, properties? Okay, so the first objective in this lesson is converting between exponential and logarithmic forms of equations. So basically, you're going to have an exponential equation and you're going to have a logarithmic equation. So the exponential one looks like b to the x equals a. And this corresponds to the logarithmic equation. Of course, you have the word log, and the base of the exponent is the base of the logarithm, and the a is actually inside the log equals x. Now, you must know this. So unlike other definitions that you kind of just have, sort of know, you're going to be using this definition. So do you notice the parts here? The base of the exponent is the base of the log. And the power of the base is what the logarithm is equal to. So what we're going to do is we're going to complete a table and we're going to practice converting. So we have exponential equations. So we know that 2 cubed is 8. That's an exponential equation. How would you write that as a logarithmic equation? Well, for sure you have the word log, right? So what would be the base of the logarithm?
Would it be 3?
2. The base of the logarithm is the base of the exponent. The base of the logarithm is the base of the exponent. So what's inside the log? It's what the exponents, it's what the thing's equal to, right? The equation?
8.
Equals. So that's how you write the log equation. That's correct. So let's do this one. This was a property that I gave you. Log base 6 of 1 equals 0. So what does that look like in exponential form? What's the base of the logarithm? Guys,
The base.
you're just following this rule and you're putting it in the form, okay? So look at the parts. The base of the exponent is the base of the logarithm. What this is equal to is inside the log, and the power is what the logarithm is equal to. So how would you write it in exponential form?
6 to the 0 power equals
6 to the 0 equals 1. And doesn't that look familiar to you? Because didn't we say that any number 5 to the 0 is 1, 7 to the 0 is 1, 20 to the 0 is 1? So now you know why this is a property. Because any number except 0 to the 0 power is 1. That's where the property came from. All right. So what about 4 squared equals 16? That's an exponential equation. How would you write that as a logarithmic equation? Well, you need the word log. Log base what?
4.
Base 4.
Uh-huh. Of what?
6.
16
Oh, sorry.
equals 2. So log base 4 of 16 equals 2. A minute ago, I gave you this property. Log base 12 of 12 to the 1, or yeah, 12 to the 1 equals 1. How do you write that in exponential form?
Is it 12 to the power of 1 equals 12?
Yep. And now you know why that's a rule. Because you know that any number to itself, except for 0, any number to itself, I'm sorry, any number to 1 is itself. And that's where that log base b of b to the x equals x comes from. Okay, we'll do one more. So there's your exponential equation. How do you write that in logarithmic as a logarithmic equation? Log base what?
Log base 2/3.
Uh-huh. Of what?
of Q.
Right. Q equals P. All right, any questions about how to convert from an exponential equation to logarithmic and back again? You're gonna have to memorize the definite definition. All right, let's go to the second objective. The second objective is evaluating, which means find a number. So we're going to evaluate logarithmic functions. By thinking in terms of exponents. And I'm kind of distracted. I just want to ask you guys a question. Do you think you could have taken this class during summer? I know I couldn't have. There's no way I could have taken this class during summer. And now what they're asking you to do is to take pre-calculus during summer. All right. So if f of x equals log base 10 of x, they want us to evaluate by finding f of 1,000, f of 0.01, and f of square root of 10. So we're going to do each one of these, and I'm going to show you how you do it. We're going to use the function they give us, log base 10 of x, and we're going to put in on the first one 1,000. And wherever you see an x, you're going to put 1,000. And here's what I want you to keep in mind. I want you to keep in mind that property that I haven't taught. I'm going to write it up here. It's actually an inverse property. So remember, when the base of the exponent equals the base of the logarithm, they undo each other because they're inverses. They cancel. So what you're trying to do is you're trying to make 1,000 look like 10. So watch. Isn't 1,000 10 cubed? And can't we use the property now? Isn't log base b of b to the x, x? And doesn't evaluate mean find a number? Yes, no?
Yeah.
Let's do the next one, b. We have the same function, log base 10 of x. So they want us to find f of 0.01. So wherever you see an x, you put 0.01. Now, we want to make 0.01 equal to 10. So we're going to change it to a fraction. And now we're going to use the negative exponent property to get them on the top. Remember that? Put them on the top and make the exponent negative. And then we're going to take the 100 and make it 10 squared. And then we're going to multiply the powers. And then we're going to use the property. Now I want you to notice that this is a 6-step problem. And that's why we're doing it in chapter 15. So I'm just letting you know, the students who skip steps will not do well on this test. You must show what you're doing from one step to the next. So I'm going to go over it if you want to watch. I substituted in 0.01. I changed 0.01 to 1 over 100. I used the negative exponent property to flip them on the top. I wrote 100 as 10 squared to the negative 1. I multiplied the powers using the property of exponents, and then I used that property to evaluate. The last problem, we're using the same function, f of x equals log base 10 of x, and we're evaluating f of square root of 10. Now, remember in the one chapter when we changed radicals to rational exponents, remember that? That's what we want to do. So remember that square root of 10 is equal to what, class? 10 to the 1/2 power. Remember that? So log base 10 of 10 to the 1/2 is 1/2. All right, does anybody have any questions about any of these steps? I'm going to do one more problem like this. Questions? Okay, can I erase this then? Can I erase this one? Yes. Okay. So if we have f of x equaling log base a half of x, they want us to find f of 4, f of 1 over 32, and f of 2 radical 2. So in the first one, we write down the function log base a half of x. And we're going to put in 4 for x. So this would be log base a half of 4. And remember what we're trying to do. We're trying to make the 4 look like a half. Well, hold on a second. Shouldn't I flip him to the bottom and make him negative so we at least have a fraction? And then can't 1/4 be written as 1/2 squared to the -1? Are you seeing how careful I'm being about my notation? And wouldn't this be log base a half of a half to the -2? So wouldn't the answer using the property just be -2? Follow that? So we're trying to make the 4 look like a half. So we flip them to the bottom using negative exponents. And then we know 1 squared is 1, 2 squared is 4. So after that, we're going to multiply the powers, and then we use that property. So in the next one, you're using the same function, log base a half of x. And this time, we're evaluating x being 1 over 32. So this would be log base a half of 1 over 32. Well, it's already a fraction. How do we make 1 over 32 look like 1/2? We just write that and put it to the 5th power, because 1 to the 5th is 1, 2 to the 5th is 32. And so what's our answer?
Five.
5. Okay, one more. You might want to watch this one and then write it down. So in this one, we're going to evaluate f of 2 radical 2. All right, now. The first thing we're going to do is we're going to change radical 2 to 2 to the 1/2 power. Now, when you do that, do you remember when you multiply monomials with the same base, you add the exponent? So don't you need a common denominator on the other guy? So don't you have to write this as 2 over 2? So wouldn't that be 2 to the 3/2 power? So now, can't you put him on the bottom with a negative exponent, and that's going to be raised to the 3/2 power? So isn't this going to be log base 1/2 of 1/2 to the negative 3/2 power? So your final answer is negative 3/2. Six steps. So you substitute in for x. You rewrite the radical using rational exponents. You know the property says that when you multiply monomials with the same base, you add the exponents. That's why you need a common denominator. So you get log base 1/2 of 2 to the 3/2. You have to flip him to the bottom using negative exponents. You multiply the powers, and you use this property, log base b of b to the x equals x. All right. Any questions? So like I said, this is really requiring that you're able to work through a process, that you're able to be, you're able to be methodically thinking through a process, because there's no way you're going to get that answer unless you know exactly what you're doing. All right, let's go to objective 3. It's evaluating logarithmic functions using a calculator. And let me just say this. You never use a calculator unless it tells you to, or if it's some type of problem where you know you can't do it by hand, but everything has to be done by hand. So you cannot use a calculator unless they explicitly tell you to. All right. So first of all, I want to define a common logarithm. You will never see this. What you're going to see is this. So in other words, the 10 is invisible. Like 1x equals x. This is, don't read, this is log of x. This is log base 10 of x. Log base 10 of x. That's called a common logarithm. There's also a natural logarithm. And the natural logarithm is log base e of x, but you're never going to see that. What you're going to see is this. And so in your brain, when you see this, it's called a natural log of x. It means log base e of x. So this means log base e. That's not an I, by the way, that's an L. So it's a natural log of x. It means log base e of x. Now on the calculator, this is going to be the log key because your calculator is base 10. You don't have a base 2 calculator. You don't have a base 3 calculator. And so if we have other problems, I'm going to have to show you how to convert them to base 10 because that log key on your calculator is base 10. The natural log looks like ln on the calculator. So let's work with the calculator for a minute on some problems that are impossible to do by hand, pretty much. All right, so they want you to use a calculator, and they're going to give you a number. And they want you to find the logarithm of 13, log base 10 of 13. So put it on the calculator, log base 10 of 13, and tell me what you get. Go ahead, I'm listening. What do you get?
1.11.
Don't round too much. 34943. 113943. Don't round too much. Now, what they're asking in this problem is they're asking you to use exponents to verify. So you know this is base 10, and you know that this is what the power is, and you should get something close to 13, right? So 10 is the base, that's the power in exponential form, and we should get something close to 13. What did you get?
12.999.
And that's close to 13, right? All right. So in the same problem, they want you to do the natural log. So I want you to put that on the calculator and tell me what you get. So what's the natural log of 13?
2.5649.
4949. And then they want you to use the exponential form to verify. So the base of a logarithm is e, the power is going to be 2.5649, and it should equal something close to 13. So what did you get?
12.999.
And let me just say this. If we did not round so much, we would have got 13. So that's what I'm saying. When you round, like when you cut the number off, we came close, but if you had run out more digits, you would have got 13.000 something. Okay, let's do another one of these problems. They're asking you to use the calculator to find the logs and then use exponential equations to verify or prove. So how about this number, 0.42? So you want to find the log base 10 of 0.42 and tell me what you get. What'd you get?
I got negative 0.376750.
And so we're going to use an exponential equation to verify this. So the base is 10 to the negative 0.37675070, and tell me what you get. You should get something close to 0.42. What'd you get?
Point 0.420000 and then 93.
Yeah. So if we take the natural log of 0.42, go ahead and tell me what the calculator gives you with that one.
Negative 0.86750.
500. Well, yeah, probably shouldn't round that much. I don't have any room on my board. So the base of the natural log is E. We're taking to the negative 0.86750. And what do you get? You should get something close to 0.42.
I got 0.42000 and
That's okay.
0238. Yeah.
Close enough. Okay, any questions about how to use the calculator with the common logarithm or the natural logarithm? This one's base 10, this one's base E. Also, I think I mentioned this before, but I did include a paper about logarithms in your assignment. Like, what is a logarithm? How is it used today in real life? Like, when would you use a logarithm? So it's kind of an interesting paper if you want to read it. All right, let's look at some practical problems. The first problem has to do with chemistry. It's on page 752A. So I'm going to try to read it. I hate chemistry, so bear with me. The acidity level or pH of a liquid is given by the formula pH equals that stuff, where that notation is the concentration in moles per liter of hydrogen ions in the liquid. In a typical chlorinated swimming pool, the concentration of hydrogen ion ranges from that number moles per liter to that other number moles per liter. What is the range of the pH for a typical swimming pool? So they give us that the pH is equal to log base 10 of 1 over this notation. Now, this notation, as explained in the writing, is the concentration in moles per liter of hydrogen ions in the liquid. So what we're going to do is we're just going to plug in the numbers. So this would be the pH is equal to log base 10 of 1 divided by The first number was 6 in scientific notation, 6.31 times 10 to the negative 8. Now listen carefully. I would put this in parentheses to make the calculator work right. Last period, well, you want to, if you have 3 left parentheses, you need 3 right parentheses. If you have 4 left parentheses, you have to have 4 right parentheses. Last period, somebody left off a parenthesis and got the wrong answer. So to make the calculator work correctly, I would put that in parentheses and tell me what you get. So it's log base 10 of 1 divided by 6.31 times 10 caret negative 8. Anybody get it? It's about 7.2.
Yeah, I got that.
How about the rest of you? Were the rest of you able to get it?
Yeah, I got it.
Yeah, I got it.
So now we turn around and do the same thing with the other number. So the pH is equal to log base 10 of 1 divided by 1.58 times 10 to the negative 8. What did you get for that one?
I got 7.80.
Yeah. So your answer would be the pH of the pool. It ranges from 7.2 to 7.8. That's the pH. So pretty easy. It's just putting it in the calculator correctly. Now this next problem, you might want to just watch and then write it down later, because there's going to be some stuff I'm going to do that you've never done before. And so you might want to just watch it. Can I erase this one? All right, it's page 752B. It has to do with biology. The Lactobacillus acidophilus is one of the bacteria used to turn milk into yogurt. The population P of a colony of 3,500 bacteria at time t in minutes can be modeled by the function that how long does it take the population to reach 1,792,000? All right, so we're going to write down the formula. P of t is equal to 3,500 times 2 to the t over 73, where t is in minutes rather than hours. Because usually t is in hours, but t is in minutes in this problem. Now let's talk about this. they want to know what t is. And t is an exponent, and we got to get him down from there. So how we're going to get him down is using the inverse, which is the logarithm. So remember the logarithm and the exponent, the base of the exponent cancel each other out, right? Okay, so I'm going to isolate the variable. So, and by the way, I'm not going to plug in that 1 million right now. I'm going to wait a little while because I don't want to be writing 1 million, 1 million, 1 million, 700, whatever it is. I don't want to write that. So I'm just going to leave it as P for now, divide by 3,500 because we're isolating the variable. And it's like, okay, how do we get them down? And what we're going to do is we're going to take a log base 2 to both sides. Now, if this, pay attention, if this had been a 7, I would have taken a log base 7 to both sides. If this had been 1/2, I would have taken a log base 1/2 to both sides. So what you have here is you have this, which just allows us to get the power down, right? Log base b of b to the x equals x. Log base b of b to the x equals x, right? And over here, we have a mess. Okay, so what we're going to do now is we're going to plug in the big number. And the big number for the population was 1,792,000, and it's going to be divided by 3,500. Now, pay close attention to what I'm going to say right now. We can simplify those numbers. But if we had this, you cannot simplify that. That is not a 10 and a 5. This is log base 10 of 10, which is 1. So that's not a 10. So you can simplify something like this, but don't ever try to simplify something like that. In other words, when a number is inside a logarithm, he's protected. You can't touch him. Now look at this. You can cancel the trailing zeros, and on your calculator, tell me if 17920 is divisible by 35.
Yeah, it's divisible. It's
What is it?
512.
So I just switched sides. Put this over here. I can do that with one of the, I think it's the reflexive property. So now we can't put this in the calculator because it's not base 10. So watch what I'm going to do. So I haven't taught this yet, but there's something called a change of base formula. And what the change of base formula allows you to do, look up here, please. You can write this as log base 10 of 512 over log base 10 of 2. So that's pretty cool because now we can put it in the calculator. Okay, don't write anything. Watch this. Log base 1/2 of 7. To write that using change of base, you would say log base 10 of 7 divided by log base 10 of 1/2. So it's really easy formula. Log base 12 of, I don't know, 3. It's equal to log base 10 of 3 divided by log base 10 of 12. So the change of base formula is really easy. It's really nice. And remember, you cannot simplify that, right? Because you can't touch those things inside the logarithm. All right, so we're almost done. I'm going to multiply by 73 on both sides. And now you're going to put that in the calculator. So listen to how you're going to do it. You're going to take log base 10 of 512 divided by log base 10 of 2, hit enter, and multiply by 73 and tell me what you get. Or if you want to do multiple steps, you guys, you can just leave this as 73 and just do that part. So what's log base 10 of 512 divided by log base 10 of 2? Come on, you guys. Log base 10 of 512 divided by log base 10 of 2. What is it?
I got 9.
So what's 73 times 9?
657.
So that's the answer. So you would say the bacteria will reach 1,792,000 in about 657 minutes. Or you could divide that number by 60 to get hours, which is about 11 hours. So the bacteria will reach that big number in about 650 minutes or about 11 hours. And I'm getting 11 by dividing that number by 60. All right, let's talk about the problem. Okay, first of all, you didn't see me plug in that 1,792 until later. So I just left it as P and I isolated the variable by dividing both sides by 3,500. So when I got here, I was like, how do I get him down from there? How do I solve for T when he's an exponent? And the answer is undo him with the inverse. So that's why you saw me take a log base 2 to both sides, because log base 2 of 2 to that is T over 73. At this point, I put in the 1,792,000 so I could simplify it. And we found out that that simplified to 512. So now we can't use a calculator because it's a base 10 calculator, log base 10. Well, this is a log base 2. So I introduced something called the change of base formula, which says you can write it as base 10 if you write 2 logs and write log base 10 of that number divided by log base 10 of that number. So then I solved for T by multiplying by 73, and I decided I wasn't going to do this all at once. I did this part right here, log base 10 of 512 divided by log base 10 of 2. Remember, you cannot cancel those because they're inside a logarithm. So we ended up with 73 times 9, which is 657 minutes, which is about 11 hours. All right. Any questions? Okay. Well, I'm going to let you go early today. Since you took that exam this morning, your brain is probably fried, especially after all this. But I did want to give this to you so you could look at it over the weekend and try to decipher what's going on. I know you haven't really ever done anything quite like this. And so what's going to happen, I'm going to in class, I hope you guys have a fabulous weekend. But any of you want to stay after, I can give you my opinion about that bridge pre-calculus class this summer. Okay, so if you got an email or a letter or whatever you got from the district, I'd like to address that with you. Everyone else you can take off if you want. If you got a letter, stick around and I will talk about this and just give you my opinion. Okay? All right, the rest of you have a good weekend. I'm going to turn the recorder off, and then those of you who want to hang out, we can.